All right. Okay, let's get started. We just glorified office hours as far as I am concerned, right? So there's nothing I'm going to do other than just tell you, look, this is a syllabus. If you have any questions, I'll answer, okay? Or if you want me to review something that you would like me to review, I'll review that, okay? So I'm not going to go through systematically all these topics because too long, right? So things that you need to know are basically what is out here, building regular expressions, DFAs, NFAs, context-free grammars, right? So if I ask for a language and say build a DFA for it, or build an NFA for it, or give a regular expression for it, or build a context-free grammar for it, you should be able to do that. You should know the relationship between regular languages, DFAs and NFAs, how you can go from one to the other. Right, the one piece we didn't cover is how to go from a DFA to a regular expression, which is a messy thing that we'll come to later on, okay? But you should be able to go from an NFA to DFA. How do you do that? Yeah, subset construction. Not just be able to do it for a given example, but actually understand the construction itself. What is the meaning of the construction, right? And you should remember, yeah.
Are you recording your lecture?
I think so.
Okay, I just wanted to make sure. So.
South projector and okay.
Oh, you know what you're doing. You should be good, but I'll just make sure. Sorry.
Okay, that's fine.
You're good. Sorry.
Okay. Yeah, no,
I
that's
just
good.
didn't want to make sure. But I think you always use the source.
Yeah, that's right.
Thank you so much.
You want to get rid of this? Okay, that's fine. Yeah,
okay.
Sounds good. Thank you. Yeah. Okay. You should know product construction for DFAs, right? And closure properties are very important, right? They help us understand how to prove interesting facts from known facts, right? And finally, proving that languages are not regular using the fooling set technique or closure property. Okay, so those are the topics for the midterm. Yeah, no Turing machines. So questions, concerns? Yeah. A proof or just a transformation or yeah, okay. So so what he's asking is I'll do it by an example so that it's the proof is also clear. So what he wants to understand or remember is if I have a regular expression or we want an NFA n such that the language of the regular expression is the same as the language accepted by the NFA. Okay, so here is an example: 1 0 plus 1 0 0 star, something like that. Okay, I'm just making up some silly example. Okay. So how did we do this? So we went back to how we define regular expressions, right? And we said, okay, how are regular expressions defined inductively? Well, they're the base cases, right? What are the base cases for regular expressions? Oops. Base cases are the empty set, epsilon, and A, right? What does the epsilon refers to the language containing the single string epsilon, right? This is overloading. A refers to the language which consists of single string A, right? Here A belongs to sigma, right? Okay, and then how a regular expression is defined, if R1 is a regular expression, then R1 plus R2 is a regular expression with the understanding that the language is R1 union R2, right? Where R1 is a language of R1, small R1, R2 is capital R2 is a language of R2, yeah? And then we can do R1, R2, which means that, the language of this is R1 concatenated with R2, and then finally R1 star, which means it is R1 star, right? So there is an analogy between regular expressions and regular languages, right? The meaning of the language for a regular expression, right? Okay. So if you can mimic this union, concatenation, and clean star using NFAs, then we'll be done, right? So if I have an example like 1 0 plus 1 0 0 star, the top level operation is union, right, or plus in this case. So if we had an NFA which accepts the language represented by 1 0, and we had an NFA that accepted the language represented by 1 0 0 star, then how do we create an NFA that accepts the language of the union, right? So, we have an NFA N1 and we have an NFA N2, right? Accepting L1 and L2, and we want an NFA that accepts what? L1 union L2, right? So we create a new start state and connect it to the start states of this by epsilon transition, right? And this is the new NFA N, right? Yeah? Okay? Yeah. No, I'm saying this is the idea, all right? So that is a high level idea, no? That's a very simple high level idea that is easy to remember. Let me get the point. You remember that? Yeah, that high level idea. Are you convinced that N will accept? Where is my pointer? Okay. All right. So if we had a okay. So this is a union. So if we could build a NFA for 1 0 and build an NFA for 1 0 0 star, then we could take those and create a new NFA which accepts the union, right? Okay. So now you have to say, okay, how do I build an NFA for 1 0? Or in general, if I have a concatenation of two regular expressions, how do I build for that? Well, if I had an NFA N1 which accepts the language of R1 and an NFA N2 that accepts the language of R2, and we want to accept the language L of R1 concatenation with L of R2, what do we do? So we have basically have one, say suppose I have 1 0 concatenated with some other language, right? 1 0 0 star or something like that. So we already built an NFA for this, we already built an NFA for this, right? So now we want to build an NFA which accepts the concatenation of these two languages, right? Represented by these regular expressions. And so we say we build it like this. It's a very visual, right? We remember we can, without loss of generality, assume that NFA has only one accept state and one, right? Do you remember that? Okay. How do you make sure that NFA has only one accept state? Exactly one. yeah, put all the accepting states with an epsilon transition to one accept state which has no outgoing transitions, right? So that makes life easy. So we can, without loss of generality, assume that we have such an NFA rather than an arbitrary NFA, so that it makes our life easy. So this one accepts L1 and this one accepts L2, and I claim that this would accept, I remove this as final state, right? This would accept N1, L1 concatenated with L2, right? So if I already built machines for this one and this one, I could just make a machine for this. Yeah. And the final thing we need to do is the Kleene star, right? So I want to say, create something like this, right? So I already suppose, what is an NFA which accepts 1, 0, 0? Very simple, right? 1, 0, 0 is just this, right? This is an NFA which accepts 1, 0, 0, right? Nothing else, yeah? Okay, now I want to create an NFA which accepts the star of this, right? Right? So the natural thing to try is to say, okay, I'll take a epsilon transition back to the start state so that I can go round and round, right? Okay. So you have to be a little bit careful, because in a general NFA, if you go directly to the start state, that start state may have incoming transitions and you may run into some trouble. So the idea, general idea, is that I have an NFA which looks like this. What I should do is create an extra start state and then copy this and come back to this and make this the accept state. Okay, because we need to accept epsilon in the Kleene star, right? Okay, so this is what we need to do. We take this NFA, which is N, which accepts L, and this is N prime, which accepts L star. Okay, we create an extra start state connected to the old start state with an epsilon transition, and from the final state of N, we create an epsilon transition to the start state. Okay, so it's very mechanical, boring, right? If you want to do it for an example, it's boring, but high level, it's nicer, right? Okay, so you have to do this recursively, right? If you had something like this, you first create something for this, then you do this, and then you apply this operation. And then you say, how do I create something for this? You say, this is a concatenation, so I know how to do concatenation. So it's like a recursive algorithm, right? But the definition is inductive, the algorithm is recursive. Yeah? Questions? Yeah. All right. Next. Yeah. Can I do some problems on closure properties? Maybe it should be more specific. So maybe it'll help have a concrete question. Yeah. Okay, let me give you a good, not a concrete example, but why it's dangerous. Okay, so it's good to understand. I asked you to do it as an exercise, probably no one did, right? Suppose I have an NFA which looks like this, right? This is the start state, right? Okay, see, the reason why the reason why it is dangerous is because we are making this an accept state. That's the reason why it's dangerous, not because we put an epsilon transition back from the final state. So let's see. Suppose we had something like this, right? I'm drawing some abstract machine, which I can make concrete if I want, right? And something like this, right? Okay. Now, so take this, right? 1, 0, 1. 1 or something like that. Okay. Now this accepts some language, right? I don't know what it does, but it accepts some language, right? But now suppose I put a epsilon transition back to Okay, now so let me know. So suppose I put an epsilon transition back from this state, right? Now, if I make this an accept state, okay, what will happen is even forget about this epsilon transition. Previously, 101 was not in the language, right? But now you're making it part of the language, okay? No, so this would work if the start state of the current NFA has no incoming transitions. Okay. Yeah. Yeah, that would work too. Yeah. 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 Because in some sense, if you're not doing anything right here, right? You're just going back to this. Yeah. So it would work too. Yeah. But the dangerous part that you are careful about is that if the old start state had incoming transitions, then you may accept strings now because you made it accepting. So that's the only reason to be careful. Okay? Yeah. Yeah, so let me get to his question first and then I'll come to that. So closure properties. Okay, so the basic closure properties that you should remember are that the definition of regular languages are like basic things are they're closed under union, closed under intersection, closed under complement, right? They're very important, right? Because these are the simplest things. If you design a DFA for a particular language and suddenly you want to create a DFA for the complement, you don't have to think. It's a very nice, powerful tool, right? It's not just for proofs, right? It's like I wrote code for something. Yeah, I can easily write code for accepting the complement of the language, right? Or if you want to design a DFA and you're thinking, how should I design a DFA? Oh, why is it regular? And you say, wait a second, I can express these strings. This is a complicated language. You can't quite wrap your head around it. And you say, no, this is easy if I can express it as a union of L1 and L2, right? Because and or are things that we are comfortable with, right? Accept all strings which either have 374 or 473. That's the thing that we think about, right? So if you had the power to say, look, I can design a machine just for 374 and just for 473 strings that contain them, and if I can take the union and that is regular, it's automatic, right? It's like a programming language, right? Ands and ors and complements are very powerful tools to allow us to combine code or algorithms for individual things. Okay, so those are basic closure properties, right? We saw that in some detail, and you can use them into design languages and to prove properties also, right? If you already have some existing results, you can use them to prove new properties, right? So they have two advantages: one, building things, and in now the thing is, regular languages are closed under many more interesting properties, right? Which don't look that natural or apparent at the outset, right? Like reverse or prefixes or suffixes, right? How do we see that? Part of the reason why we kind of make you do those things is to get you comfortable with formal reasoning. It's not that all of them are very interesting or something in practice, right? It's just to make you get more rigor in your understanding of the basics, so that when you do this more difficult or non-trivial closure properties, you say, now I understand DFAs better, now I understand NFAs better, or now I understand the proof techniques better, right? And some of these are just playthings, right? They're not particularly, they don't come up in regular usage all the time. So now the question is, let's take a concrete example, right? I'm trying to see, I could do something from the lab, or I could do something from the homework, or I could do something new from the what you call this study problems. If some of you want to pick some problem from there, I can try to do that, right? But let's see, why, okay, let me ask you this question. I think we kind of briefly did it. If I have a DFA or a regular language, it is closed under reverse. What does that mean? I want to take a language, and what is the reverse of a language? It's all the strings which are the reverses of the strings in the language, right? So that's a regular too. Why is that, right? Okay. So let me state it again. I give you any regular language L. Now define the reverse of a language as all strings which are reverses of the strings in the language, right? So what's an interesting example for fun if you want to do it, right? Suppose you design a language for all strings that end in 001, right? And then you say, what is the reverse of that, right? The reverse of that is all strings which start with 100. Okay, sure, we can design a DFA for that, but without thinking, we can say it is regular too. How can you prove that? Okay, so the important thing here is the fact that it's a for all statement, no? It is not a specific language we need to prove it for, right? It says, that sometimes trips people up. We want to say something like this, right? For all L such that L is regular, reverse of L is regular, right? That is really what we're trying to prove, right? Okay, this is a little tricky because, I don't have the L in my hand, right? I don't know what L is, right? So it's a meta statement, right? We need to prove it in a generic way, right? Not like, look, I have a language, L is, particular language, now I have a DFA for it, now I'll design a DFA for the reverse of that language. That will only prove that the reverse of a specific language is regular. Here it is saying for all regular languages, the reverse is also regular. Yeah, so basically to prove something like this, you have to prove a meta theorem which doesn't rely on the specific language's properties, but it simultaneously shows it for all regular languages, right? So we have some tools, right? How do we design, how do we think of a regular language? We say, what is a regular language? Now you have three choices to figure out what is the most convenient form to use. You can use the inductive definition using regular expressions in the terms of how we define, or you can use DFAs, right? What does it mean for a language to be regular? It is precisely the set of languages accepted by DFAs. So you can say, if it is regular, then there is a DFA. So if I can take the DFA and give a new DFA for the reverse of the language, then I'm done, right? Okay. Or I can use NFAs, right? You should not try to use NFAs because they are the most powerful. So in terms of expressivity, but they have the least properties for that reason, right? They are more complicated. So if you want to constrain yourself. So when you think of L as regular, you should not try to say, it has an NFA, because that means that the NFAs are more complicated beasts, right? So you say, let's restrict it because the behavior will be restricted. So DFAs are more convenient to assume that they are, but you can use NFA to prove that reverse is regular. So you make the initial assumption as tight as possible, so that and you give yourself the freedom to use as much power as possible, right? That's always nice, right? So here are two ways of proving it. Okay, you can use both using DFAs, and you can also prove using regular expressions. Okay, suppose L has a regular expression. How can we create a regular expression for the reverse of L? Right? If L is regular, then it has a regular expression, right? Now I'm claiming that we can create a regular expression for the reverse of L. That would mean that it is regular too. Okay, it's hard to do it with a fixed regular expression, but let's try again inductively, right? We have to understand if I have R1 is a regular expression and R2 is a regular expression, and I can create the reverse of R1 using a regular expression and the reverse of R2. Can we do it for R1 plus R2? Okay, so let me write it. So there are two proof techniques. Let me give you two proof techniques here, okay? One, L is regular implies L is L of R for some regular expression R, right? Yeah? That's okay? Okay, No, but how do we use that information to create? So what do I need to prove? Need to prove or can prove there exists R prime such that reverse of L is L of R prime, right? If I can do that, I am done, no? Using the regular expression for L, if I can create a regular expression R prime for the reverse of L, then I am going to prove to you that reverse is the reverse of a regular language is regular, right? Yeah. Okay, but how is R? I mean, okay, again, you know, R is abstract, right? So we have to say, how did R come about? R must be either R1 plus R2 or R1 R2 or R1 star, right? And inductively, we can do induction on the size of the length of the regular expression and say, aha, if R is R1 plus R2, I know how to create regular expressions R1 prime and R2 prime such that R1 prime captures the reverse of the language defined by R1 and R2 prime is captures the reverse of the language captured by R2. Now can I capture R1 plus R2, the reverse of that using R1 prime and R2 prime? What is it? Okay, so more precisely, R1 prime is such that L of R1 prime is reverse of L of R1. Okay, and same R2 prime is such that L of R2 prime is the reverse of L of R2. Suppose I do inductively figure it out, right? Now how can I, but my R is R1 plus R2, right? So what is the reverse of R1 plus R2? The language captured by reverse of R1 plus R2, yeah? I claim it's R1 prime is R2 prime. What do you have to think? Okay, it's a union, okay. You have to, I mean, it is, you have to make sure that you understand that. You can say, okay, is it true that if R1 prime captures the reverse of L of R1 and R2 prime captures the reverse of L of R2, then the reverse of L of R1 plus L R2 is actually captured by R1 prime plus R2 prime. It is, but you should stop and think. That's right, you know, say, yeah, okay, you know, all the strings in the reverse of R1 prime are there in R1 or in R1 prime, and all the strings which are in, you have to make sure that you understand the union operation and say this is a safe thing to do, right? And it precisely captures what you want, yeah? No, not to prove. See, you know, you all of you think that the proofs are because the instructors are like, you know, crazy, right? The proofs are not for me to check. It is for you, right? How do we think? Without proofs, we make up things, right? You know, I can make up whatever I want, right? You know, there is no way that we can do any formal, interesting stuff without analytically pausing and saying, am I doing sensible things or am I just fooling myself? There is no way. Anything serious, right? Anything serious in reasoning. You know, your code is not some random stuff, right? You are trying to write code or build a system to do something correctly, right? Maybe, you know, your homework assignment is not critical, right? But tomorrow, you know, you will be writing some code and, you know, you'll send the Mars Pathfinder, it will crash, okay? Why do we, the whole point of writing software or designing systems so that they actually work the way they're supposed to work, right? And we are very good at fooling ourselves into believing anything that looks plausible, right? But believing something that is plausible, if you don't have any check on that, what is a check? The check is not necessarily always a formal proof, but the check is doubt, right? Okay, how do you act on a doubt that am I correct at all, right? Well, you know, or even to explore a space, right? Should I do R1 prime plus R2 prime or what, right? If you don't pause and think and say, I should verify that a little bit, then you can believe whatever you want, right? The point of proofs is not to convince some instructor or something like that. The point of proofs or thinking about proofs is to convince yourself that you're on the right track, right? If you don't, you won't know, right? You design a DFA. Why is the DFA correct? At least you should say, do I understand the meaning of the state? If I don't, even if I don't, then it seems plausible, but how do you know? Right? Okay, you will say, oh, look, how do I write code? I run it on some random test examples, and if it works, I'm happy, right? But that's not enough, no? If it is important code, you have to pause and say, how do I verify some properties of what I'm going to do and put that into my code or assertions or something so that I have higher confidence that I'm doing what I'm supposed to do, right? The proofs are not, don't think of proofs as something that this 374 instructors are crazy about. They're not, right? We all make mistakes in thinking, and that's why they're important. Okay, enough philosophy. Okay. So what about R1 prime and R2 prime? What about concatenation, right? If R1 and R2 are regular expressions and I am interested in, so I have a reverse of R1 prime and R2 prime, what should I do? What is the regular expression for this, reverse of this, knowing that the reverse of R1 is captured by R1 prime and reverse of R2 is captured by R2 prime? R2 prime, R1 prime, okay? Now, some of you might think it's R1 prime, R2 prime, no? It seems like roughly plausible, right? Or so you have to pause and say, is it R1 prime, R2 prime, or R2 prime, R1 prime, right? You have to verify, are all the strings in my language exactly captured by R2 prime, R1 prime, and vice versa, okay? It's important to pause and verify that, okay? Now, I won't do it, but you can verify it, right? It seems plausible, right? Yeah? And what about R1 star? If I had R1 and R1 prime and I want to capture the reverse of the language R1 star, what should I do? Is it R1 prime star? Yeah? Okay. R1 prime star should be the, yeah? Okay, but it seems a little bit more doubtful, no? Yeah, it seems like, maybe it's fake. Okay, that's good. That means that, we are not quite sure, right? Okay. If you're not quite sure, then you have to kind of expand the definition of it, make sure that all the strings in the reverse of all the strings in R1 star are actually in the language R1 prime star and vice versa, right? What is the definition of cleany star? Right? What is the definition of cleany star, right? What's in this? What are strings in R1 star? So it is the union, right, of L of R1 to the k greater than or equal to 0, right? Any number of concatenations, right? Okay, you should go stop back and say, okay, that is what this language is. Now you can ask, now you can understand what is the reverse of this language, right? What is the reverse of this language? Okay. Okay, now fix a particular, so now that's also a bit hard because it's a union of many things. So fix a k, right? What is fixing k means? That I'm looking for k strings of the form which are k concatenations of strings from L, right? Okay, now we think of the reverse of that. Okay, what does the reverse of that look like? It is going to be the reverse of L1 concatenated k times, right? Okay, then say, is that captured by my language? Yes, yeah, that is captured by my language. Okay, and you have to go the other way too. Whatever I'm in this language, they are also in R. Reverse of that is in the R1 star. So you have to, if you're not sure, this seems plausible, I have to do it too. I am in the same boat as you, right? So I pause and say, wait a second, let me check whether these two languages are the same. What does it mean? Okay, what strings are in this language? I go and say, these are the strings in this language. What should they capture? Reverse of that. What does it mean? Okay, and then I check that these two languages are the same, right? So it is going from plausibility to verification so that I'm not misled, right? That's all we are trying to do. Okay? Okay, so that's the other. What is the other proof? The other proof is via what are called, so I can assume that if L is regular, then there exists a DFA M such that L is L of M, right? Now I want to accept, so what do I want to prove? I want to prove reverse of L is regular, okay? So I can give you an NFA or a DFA for the reverse of L, then you'll be happy, right? Using M, I can give you an NFA or DFA, right? Okay, NFAs are easier for me to design because they are more, I can add epsilon transitions, I can do funky things with them. While I'm going to restrict my attention to DFAs for L because they are much more, I can easily understand their behavior because they are deterministic, okay? So it's helpful to constrain our assumption of L being regular to saying that they have a DFA, but to prove that reverse of L is regular, I can use an NFA in the design thing because I get more freedom to do that, okay? So how can you design a new machine, say NFA N, that accepts the reverse of the language accepted by M, right? But then you have to say, why is M accepting my language? What strings is M accepting? All the strings which start at the start state of M and go to the some accepting state of thing, right? So what should I accept? Only strings which are the reverses of those strings. No? That's what I'm trying to capture. How do I do that? Okay, so in terms of graph reachability, a string is accepted by a DFA if there is a path from the start state on walking, it goes to some accept state, no? But I want to kind of reverse that path if possible, right? I want to accept I don't want to accept W, I want to accept the opposite of the reverse of W, right? So ideally I would like to walk back from the DFA the other way, right? To the start state, right? So the strings that I want to accept are precisely those strings which have a walk from the start state to the accept state. Okay? So what I want to accept are strings which have on the reversal of the graph of the DFA, right? Strings which go from some accept state to the start state, right? Yeah? That's precisely the reverse of L. So how do I do that? So I reverse all the edges of the DFA, yeah, okay, and then my new start state should be all the accept states of the old DFA, right? But I can't do that because I can't collapse them into one state, but I can create a new start state with epsilon transitions to all the accepting states of the old DFA, right? And then I make the start state of the DFA my accept state, okay? Does it make sense? Yeah? So I have a DFA. What does a DFA look like? It has a start state and many accept states, no? Yeah? Potentially. So I'm going to create, this is M. How am I going to create N? I copy this machine. I reverse all the arcs. Okay? Reverse all the arcs means that if it goes from state Q to state Q prime with on A, I change the direction of the arc. If it's a self loop, what do I do? Self loop is self loop. The reverse of a self loop is itself, right? So you just keep them there. And now I create a new start state and make epsilon transitions to the accepting states of this is my new machine N. And I can, if I want, I put an epsilon transition and I remove these guys. Okay, that's my new machine that accepts the reverse of L, right? So you can understand regular languages either via regular expressions or by DFAs and see what kind of strings are accepted by the machine, right? And then say, okay, now can I express my new language in terms of what these accepting paths are in the DFA? Okay? Okay? Is that okay? So another cute way of doing it is the following, right? Okay, without creating all this machine, I like this proof technique because conceptually it is very simple. I think I put it in one of the optional problems. Given a DFA M, right, and two states which are in the set of states, define LPQ to be what? The set of strings such that delta star PW is equal to Q. So what is the meaning of this? I give you a machine. This is a set of all strings which take you from P to Q. Yeah? Okay. So is this a regular language? Is this a regular language? Yeah, why? Because I can make P the start, I have the machine, I make P the start state and Q is the only accepting state, right? That's precisely the set of strings that this machine, the new machine will accept, yeah? Okay? So if I give you a DFA, I can, I don't know, from any state and to any other state, I say, okay, all the strings which take me to this state, to that state, that defines a regular language, right? Okay? Okay, can you express now, so, and we have regular operations, right? You can take unions, concatenations, those kinds of things, right? I want to express the reverse of the L in terms of these languages, as a union of these languages. Okay? So I claim the following, right? Which is the same as this construction, but it's kind of convenient, right? So here is M. M is Q sigma delta S, accept. Let me call M reverse as Q sigma delta reverse. We understand what delta reverse is, right? And I don't care about S and A, right? This is a machine, right? Okay, so this M prime, right? Or M reverse, right? It's a new machine. What did I do? It's a DFA, right? Because I just reversed the orientation of things, right? Okay. Now I claim reverse of L of M is union, okay, right, over QS. Q belongs to accept in M reverse. Okay, so what is it saying? Okay, what this is saying, which is we already argued this, it is saying this, what is LQS in this machine reverse? It is a set of all strings which take you from this Q start state as Q and end state as the original start state of the machine M. Okay, so these are all the strings which take you from state Q to the start state in the reverse of the machine. Okay, you take the union of this over all the accepting states of the old machine, that is precisely the reverse of L. Yeah, isn't that what we're trying to capture? Right, any string which starts at some accept state of the old machine and walks back towards the start state, right? That's precisely what reverse of L is. You could start at any accepting state, and if you can walk back to the start state, that should be in your reverse L, right? So this you can write in this, and because each of these is regular, because this is a DFA, the union is regular because it's regular. The union is a regular languages are closed under union. Okay, so here I don't have to create the machine, no. Describing the NFA is more painful, while I can use closure operations to show that this is regular and my language is precisely this, so I'm done. Okay, you don't have to go nitty-gritty into the machine all the time, right? DFAs are good because their behavior is predictable. All right. Okay, somebody wanted a question on fooling sets. Yeah. Yeah. Weak and strong induction. Okay. Take merge sort. Right. We'll come to next lecture. Okay. How will you prove the correctness of merge sort using weak induction? Right. So how does merge sort look like? Everybody knows merge sort, I assume. Yeah, you do it in 125. How does merge sort look like? No. I have an array of n elements, right? You do like okay. You say, if n equals 1, done, right? Else, okay, merge sort A 1, I mean half the array, and call this, B1, and C is merge sort A of n over 2 plus 1n, and merge BC and return that or something, right? How will you prove the correctness of this? Using induction, right? So you will say, okay, I'll do induction on n, right? Okay, but the thing is, you can't go to step n minus 1 because your algorithm is solving problems of size n over 2, right? So you need to know that merge sort works correctly not just for n minus 1, you need to know that it works correctly for all k less than n, right? So there's no choice in the matter. You can't use, right? Unless, I mean, so there is no, okay, there's a silly point, right? You can make your induction hypothesis the following, right? If your induction hypothesis is the following, that merge sort works for all integers less than or equal to n, then weak and strong induction role don't really matter, right? Because you have already folded into the statement the less than or equal to part. But that's just a syntactic sugar, right? But you see, as soon as conceptually, you need to know that merge sort works on all arrays of size less than n, no? Because you need it. For an array of size something much smaller than, it's not n minus 1, you need it here. Right? It's not really about, in fact, don't think of it as weak or strong induction. Induction is the same thing, right? It's kind of silly to talk really about weak and strong induction because it just, you really want to know that the property holds true for all the things you have seen so far, right? So by tweaking it slightly, you can make strong induction weak induction. But our emphasis on strong induction is mainly to make you not have this pattern of, oh, I need to go to n minus 1, because we rarely go to n minus 1 unless it's a really simple problem, right? Look at this merge sort. The first thing you learn about recursion is that it's not n minus 1, it is half the array. How will you prove it by induction if you use weak induction, right? You can't do it, right? So yeah, it's syntactic, it's not, you think of recursion as like breaking the problem into smaller pieces, right? And the piece size is not n minus 1, it could be much smaller than n minus 1, in which case you need strong induction. Okay. So I don't know if there's a concrete example you had in mind, but really, I don't know if this convinced you. Because you can, but that is already implicit, in strong induction. Because you see, for any k less than n, you have the induction hypothesis is true, so you can apply it for k n minus 1 too. Right? So you're not losing anything, and we are trying to make you not go into bad habits. So we make it a deadly sin, not because, it's just to make sure that you shouldn't think only about one step at a time. You should think about making big steps at a time. So when you think algorithmically, it's even more important, right? So, yeah. Sorry? I'm not understanding the question. DFA takes something as it's not any well-formed question, so I can't give an answer if I don't understand what. Empty set. Oh, David, accept this. Oh, I mean that you can just do this, no? One state. There are no accepting states, so it doesn't accept anything. Right? Yeah? Is that what you can? Yeah. Yeah, fooling set question. Somebody, yeah. What is it that we want about a fooling set? Okay. Give me an example problem that seemed tricky. That way I can. Okay, let's do an easy one. Okay. Okay. Sorry, from the homework. What is? I don't remember what was in the homework. 0 to the n cube. Is that was in the homework? 0 to the n cube. Yeah. Was it in the homework? Right. Okay. What is a fooling set for it? Okay. When you think of a fooling set, right? I really want you to try to first, get a sense of, oh, why should this not be a regular language, right? I think, fooling set is a bit abstract, and it feels like, how can I create this infinite set in one go, right? It seems a little difficult to do it, right? So, but to get there, you shouldn't start by saying, that's what I want, so I'll go there in one step. First, you have to get a sense of, oh, why is this not going to be regular, right? Okay, and again, it's good to start from the scratch and go back to the proof technique we developed for thinking about fooling sets. It's always good to go back to that original construction. We say, okay, if I believe this is not regular, then my proof should go like this, right? Suppose it is regular, okay, what does it mean? There's a DFA with some number of states for it, right? Okay, well, okay, that means that, it doesn't need much memory other than the number of states in the DFA, right? Say, okay, can I recognize this language using a small number of, a fixed number of states? Okay, it doesn't look like that because n cube requires that, I somehow keep track of, if you look at n cube, that means that I accept 0, I accept, 0 to the 8, I accept 0 to the whatever, right, 27, right, and so on. And how will I remember that without kind of counting, right? That's the intuition you should have, right? And so if I can't do that without counting, that means if I give you a DFA, I should, if I give it a long string of zeros, it should get confused, right? Okay? That's the intuition you should develop, right? So what does it mean to be confused, right? So we can say, okay, if the DFA has some k states, and I give, 0 to the something much bigger than k, something like 0 to the 5k, and I give something which is like 10k, what happens to the DFA? It gets, after seeing too many zeros, it will be for some two strings with same number of zeros, it will be in the same state, no? Because it has only k states. If I give longer and longer strings of zeros, it will get into the same state, and then it gets confused, right? Because from there, its behavior cannot be different. Right? If two strings take the DFA to the same state, after that it cannot tell them apart, right? Because the DFA cannot remember anything after that, right? Okay. So if you can confuse the DFA on two strings it should not be confused about, then you can fool it, right? Okay. So your first step is not even to worry about infinite fooling set, but you say, can I create two long strings such that the DFA can be fooled with that? Yeah. Okay, so you say, okay, I do know that if I take a really long string bigger than the number of states, then there will be two such strings which will go to the same state, right? So I say I don't know what they are. Maybe this is 0 to the I, 0 to the j, right? Right? Okay. Now is it dangerous for the DFA or not? We have to figure it out, right? So it may not be dangerous, right? Because it doesn't need to remember information. But if I have two strings I and j, 0 to the I and 0 to the j, and a DFA goes to the same state, is it bad? It is bad, right? Why? If I is not equal to j, what happens? You have to see, is this right? I'm not assuming anything other than I not equal to j. Two strings got confused by the DFA into the same state. That will happen if the DFA has a small number, it has a fixed number of states, right? Now the question is, why is it bad for the DFA with respect to this language? It is bad only if somehow, there is a suffix such that, this should go to the accepting state and this should not go to the accepting state, right? Can we do it? I mean, it depends on the language, right? Okay. And what do we want, right? What we want is, can we add a suffix 0 to the IW and 0 to the JW such that only one of them is in the language, the other is not in the language. If that happens, then clearly the DFA got fooled, and right? Okay. So can we do it? Right? Okay, we do know that one of them has to be in the language, right? Well, I mean, how can it be in the language only if the I plus length of W is what? Some cube, right? Okay, it has to be some n cube, and J plus length of W should not be a cube, right? If that happens, then the DFA gets fooled, right? So just then we play with it. How can we make I plus W to be n cube, right? And how do we make J plus W not to be n cube, right? So then you need to understand what the properties of cubes are, right? Okay, so it turns out that, if you choose how can we do this? Can we do this? Yeah? How do we do it? Yeah, so you can do it if you can make I plus 1 cube. So, can we make this, we want to go to the nearest cube, right? And let's see how to do that, right? So we want to claim that, so I is here, J is here, right? We want to add some number k such that this is n cube and this plus k is not equal to any cube, right? All right. Okay. So where are the cubes? Well, the cubes will. So look at the nearest cube to I, right? There is one such thing, right? Find the smallest cube. That is right, bigger than I, right? What will that be? That's kind of hard to make sense of, right? So, in fact, you can make this argument work, but it turns out to be more clunky, right? To choose this I and J in arbitrary fashion, right? So the better strategy, is that this proof also will work, but it's a very slow and painful process, right? So instead of doing that, I could, if I choose my I and J to be somewhat more clever, right, then my proof will become a little easier, okay? So that's why I would choose not just any I and J, but I will choose my strings themselves as cubes, okay? So I'm choosing the intuition would be that, I should confuse the machine by taking two very long strings which are bigger than the number of states the machine has, okay? Now, and can we fool the machine with that by adding a suffix? Yes, we would be able to. If we do that, then we'll get a proof. But the algebra for this language turns out to be a little difficult if you choose this I and J without any properties, okay? So it turns out to make life easy if you choose strings of the form which are already in the language, okay? So if you choose these two type of strings, then we can make the proof of adding a W and distinguishing them easier, right? So if I and J are different, can we add a string W so that this is in the language and this is not in the language, or vice versa, right? What should you add to make this part of the language, right? Well, this should be, so I cube plus k should be some power, right? And j cube plus k should not be a cube, right? So what is the nearest cube to I cube? I plus 1 cube, right? How much should I add to make I cube I plus 1 cube? Well, 3i square plus 3i plus 1, right? Okay, that would make it I cube. And if somehow I get lucky and I add this to j cube and I don't get a cube, then I know that it won't be in the language. Okay, can we add this to j cube and see whether it becomes a cube or not? Well, it won't add it because I cube and j cube, j is bigger than I without loss of generality. So j cube is strictly bigger than this. So adding this to j cube won't give us a cube. So it's not in the language, this is in the language, right? Okay. So that's how you do it, right? You first have to get a feel for, does the DFA need to remember too much information, right? And can I fool it? What strings will fool it? Okay, they have to be prefixes of the strings. Yeah. Oh, the fooling. Okay, the fooling set is okay. I just argued that if I cube and j cube are for any I and j, 0 to the I cube and 0 to the j cube are distinguishable, right? I just found two strings, right? Okay. But then I noticed that this is true for all I and j. Okay, so my fooling set is 0 to the I cube for I greater than or equal to 0. All strings which are just the language itself is a fooling set for itself. Okay, I just found two strings which are distinguishable, and then realized that those two strings can be expanded into an infinite fooling set, right? So for any I and j, I not equal to j, 0 to the I cube and 0 to the j cube are distinguishable with respect to L, right? For any I and j. So then I can take my fooling set to be all of them, no? And that is an infinite fooling set. Okay. So, but the intuition for developing fooling set should come from why can't I design a machine without memory, right? Right? DFS, right? Cannot have infinite memory, right? So they can be fooled, right? So why should this language capture something that needs to be remembered? Yeah. No, they don't have to be in the language. Right? They have to be prefixes of things in the language. Okay. And it so happened that in this case the language was itself a fooling set. But in the what is the other example that we canonically do? L is 0 to the n, 1 to the n, n greater than or equal to 0. What was the fooling set for here, for this one? It was just 0 to the I greater than or equal to 0, right? So this is not the same as the language, right? But they're all prefixes of the strings in the language. Yeah. Yes. So to prove that a language is not regular, the fooling set should be infinite. So why is that? Because what we proved is that if you have a fooling set of size 100, that means that every pair is distinguishable and the set there are 100 strings, then any DFA that accepts that language must have at least 100 states. Okay. So, but then if I have my infinite fooling set is infinite, it means that I need infinite number of states in my DFA, but my DFA is supposed to be finite. So, right. So, if I want to prove to you that a language is not regular, I have to give you an infinite fooling set, right? If you just want to prove that this language requires at least 100 states, I need to give you a fooling set of size 100. Okay. Yeah. 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 Sorry? Yeah. If you want to add 7 I cube, that 7 I cube. No, wait a second. You want to add to this. You want to add 0 to the I cube plus 7 I cube. You said. Yeah, that should work too, right? Because wait, that should work too, right? Then you'll get 0 to the 8 I cube, that is 2 I cube, and I cube plus j cube plus 7 I cube should not be a cube. Yeah, that will work, right? Yeah. So what he's saying is that how do I prove that these two are distinguishable, we added a suffix of length 3i square plus 3i plus 1, right? To make it I plus 1 cube, and then we said if you add this to j cube, you won't get a cube. He's doing actually a simpler proof, right? He says, I don't remember the formula for I cube, right? It's even easier because you don't have to remember the formula for I cube that way, right? What is it? I plus 1 cube is 3. If you forget, you can even do it more simply, right? That's the advantage of his proof, right? Does everyone see that? That to prove that 0 to the I cube and 0 to the j cube, I not equal to j, say I less than j is distinguishable, you can add I cube plus 7i cube, right? I mean, you add the suffix w, which is 0 to the 7i cube, then this will become 0 to the 8i cube, and this one will become j cube plus 7i cube. And what is this? This is 2i cube, right? So it is in the language. But what about this? Is j cube, we have to make sure that this is true. If this is k cube, then, well, you have to prove this now, right? Is this always true? Okay. Is this, you have to convince yourself that this is not true. So that requires some work too. I know, but I'm saying, sometimes, no, it's not so simple, no? It's not so simple. Okay, this is why we have to be careful. See, it could be that, this is a cube of something else, no? How can I rule out that it is not the k cube for something? Is it immediate? It could be something in between. See, j is bigger than I, no? But it could be something between 2i and I cube, no? Yeah, it's not completely obvious that this is not k cube for any k. That's what I'm saying. The burden is on you. Okay? No, but I'm saying so the idea is good, but then you say, wait a second, I can't quite finish it. Okay? So that's why we have to stop and say, right? I thought it was okay until I suddenly had a thought, wait a second, I don't quite see the proof now. You see, the first idea, we go with it, right? And then I got stuck here, right? Now, this one worked out, but I started thinking and then realized I don't have a proof for this now. Okay, so I don't know if the idea will work. You see, I'm doing it too online, right? I'm trying to emphasize this process that the idea is good, but then you can't just jump to think that this doesn't look like a cube. There's no proof right now. I don't know if it's true or not, but there could be a bad example for this. Okay, so the process of jumping from an idea to making sure it is correct requires a bunch of steps, right? You go with it for a bit and say, wait a second, I don't quite see the details of this, right? And then you say, maybe not, this doesn't work, right? Or you have to work harder on this, or you say, look, maybe I'll try some other idea. Okay? I'm in the same boat as anybody else, right? I thought it would work and I got stuck here now. Okay? Yeah? No, I can prove it to you if you want. Okay, right? If because where is it? The way I can argue is that this has to be, if this is less than j plus 1 cube, I can argue that it is not a cube, no? If this is bigger than j cube, and it is strictly less than j plus 1 cube. So it is not a cube. Yeah, I argued for myself. Maybe you skipped it, but I didn't. Okay, but that's the thing. This one, I'm not sure. Okay, right? Yeah. Okay. Sorry. Yeah. Yeah. No, no, here there are distinct strings, so I is not equal to j, no? J greater than 0, right? No, but it's true that j greater than 0, I mean, if this is 0, you will have trouble, yeah. Yeah, it may be false actually. There may be a cube. So you have to, yeah. Yeah. Sorry? No, no, no. I mean, you have to be careful. No, what I'm saying is that you can make, if you add a suffix and this becomes a cube, that is okay. How do you convince yourself that this is not a cube? That j is 20i. J is 20i. No, but no. If j is 20i, then 20i cube is 20 cube I cube. No, it's not. You see, we're stuck here because we need to know now whether this is true or not, and I can go back and work it out, but I don't know, right? Maybe there's a counterexample to this. It doesn't mean that this language doesn't have a fooling set. This particular approach doesn't work. Okay, that's all it means, right? No. Okay. Yeah, no, 20. Yeah, maybe we'll talk offline. But, yeah.
Will it be able to really use the properties discussed in class, such as like closure, or would be asked to prove this?
No, yeah, I mean, anything you see in class you can use, right? In homework you can use things like that. Right? If you can state what you remember from the homework clearly, yes, you can use it, right? We saw this in homework, so we'll use the property. That's all. If we misquote it and it's wrong, then okay. Any other question? I don't know what time it is. Yeah, somebody had a question. Last question. I can't hear you because I can't hear you at all. You're very far. I have a microphone. You don't, right?
CNF is going to be on the exam.
Sorry?
CNF.
No. CNF, the Chomsky normal forms, the normal forms of the counter-spectrograms are not on the exam.